For this lesson, we're going to look at some larger systems of linear equations and the best way to solve those. So keep in mind as we go through this that two systems of equations are equivalent if they have the same solutions. So that allows us to do some modifications that we haven't seen before. So we're going to look at some techniques to transform systems. And every one of these we're going to use to solve by elimination. So one of the techniques that we'll use is to interchange any two equations. So if I have the system x plus y plus z equals 1, 2x plus y plus 3z equals 5, and 3x plus 4y equals 5. As we're going through solving, you'll see the usefulness of this, but if for some reason I wanted to interchange the first and the second equations, I can do that. I still have the same system. It would still have the same solution. It just has a little bit different look. Another thing we can do, just like we saw with elimination in two equations, is that we can multiply an equation in the system a non-zero constant and we say non-zero because obviously if you multiply by 0, that entire equation would go away. So you would not want to do that, but I don't think you would anyway. So still starting with that same system. Let's just say we wanted to multiply the top equation by -3. And you could see down below why we might want to do that. And the third technique would be to replace an equation in the system by the sum of itself and a constant multiple. Of another equation. And this is exactly what we do when we do elimination with two linear equations. So let's say we have that same system to start with. And just for preparation purposes for what we're going to do here shortly in the future, if I call these row 1, 2, and 3, I could say my new row 2 is equal to row 2 minus 2 times row 1. So if I wanted to do that algebra over here to the side, I would take row 2 and subtract from it 2 times row 1. So basically I'm multiplying row 1 times a -2. And then add those together. The x's would eliminate. I would have -y plus z equals 3. And that is now the new row 2. And like I said, you'll see soon why we want to be able to use these techniques. So we're going to start off with our first example here. Oops. we're going to solve the system. 2x plus y minus z equals 2. X plus 3y plus 2z equals 1. And x plus y plus z equals 2. And to make things easier, we're going to call the first equation row 1, the second one row 2, and the third one row 3. And that just kind of gives us a reference to talk about those. So the first thing we're going to do to solve this is we're going to make row 1 have an x coefficient of 1. And it doesn't matter how you do that. The easiest way is to move some equations. So we're just going to swap row 1 and row 2. So now our system has those two rows swapped and nothing else changes. So now from this point forward, we refer to the first one as row 1, row 2, and row 3. So the second thing we're going to do is replace row 2 with -2 times row 1 plus row 2. So I'm going to multiply -2 times row 1 and I'm going to write below it row 2. And we're going to add those together so that x's eliminate. We get -5y minus 5z equals 0. So now our system is x plus 3y plus 2z equals 1. -5y minus 5z equals 0. And x plus y plus z equals 2. And now our third technique we're going to use is to replace row 3 with -1 times row 1 plus row 3. So multiplying row 1 times -1 would be -x minus 3y minus 2z equals -1. And row 3 is x plus y plus z equals 2. Adding those together eliminates the x again. I get -2y minus z equals 1. So now our system is this. So what we've done is made it so that only our first equation has an x. We made the top equation have a coefficient of 1 and then added and multiplied times row 1 so that the x portion of each row 2 and row 3 was eliminated. So now to move forward, we're going to make row 2 have a y coefficient of 1. And we proceed from there, getting the y's eliminated. So if I look at row 2, right now, y's coefficient is -5. I could do a swap here, but that wouldn't really help. I'd have a -2. So we're just going to multiply row 2 by -1/5. So -1/5 times our current row 2 would be y plus z equals 0. So now here's our system. And I should have specified once we fix the first row to have a x coefficient of 1 and eliminate the x's below it, we don't change row 1 anymore. Okay, so now our y is the way we want it to be. So we need below that for the y to be eliminated. So we're going to replace row 3 with 2 times row 2 plus row 3. So 2 times row 2 would be 2y plus 2z equals 0. And then here's row 3. Adding those together, the y's are eliminated and we get z equals 1. So all of a sudden we know what one of our variable values is. This is our system so far. And that gives us the first piece to our solution. From here, we will work backwards to solve for x and y. So if we go up just one row in our matrix, we have y plus z equals 0, but now we know z is 1. So we substitute that in and solve for y by subtraction, and we get y is -1. And then we go to row 1, where we have x plus 3 times y is -1, plus 2 times z is +1. And then we solve. -3 plus 2 would be x minus 1 equals 1. Adding 1 to both sides gives us x equals 2. So our solution is an ordered triple. 2, -1, 1. We go in alphabetical order x, y, z. And you can always check your answer by substituting those values into the original system. So you would go all the way back to before we ever started manipulating, plug in the x, y, and z values for all 3 rows, and as long as it comes out to be true, then you know your solution is correct. So that method is very cumbersome and you have a lot of writing to do. And I want to show you a method that's actually easier using matrices. So we're going to talk about the matrix method. With the matrix method, you simply work with coefficients and constants. And you don't have to write the equations over and over again. So we're still going to work from example 1 so that we can work the same problem. We had 2x plus y minus z equals 2. X plus 3y plus 2z equals 1. And x plus y plus z equals 2. To put that into a matrix would look like this. You just put the coefficients, so 2, 1, -1, and then we put an imaginary dotted line where the equal sign is and put our constant on the right side. So 1, 3, 2, 1, and 1, 1, 1, 2. The name of this matrix is an augmented matrix. And this particular matrix is a size 3 by 4. When we talk about matrices, just to give you a little bit of background, in case you haven't worked with matrices yet. If you have this matrix, it has 4 rows and 5 columns. And you identify it in row and column format. So the size of this one would be 4 by 5 because you say the rows first and then the columns. And then each little block where you would put a number is called an element of the matrix. So that's just some real quick vocabulary on matrices. Okay, example number 2, we're going to use matrices to solve the system. Our system will be x minus 2y equals 6 minus 4z. X plus 13z equals 6 minus y, and negative 2x plus 6y minus z equals negative 10. So for the first time, our system is not nice and pretty and in standard form. So that's going to be our very first step. We're going to put in standard form. And that just means your letters are in alphabetical order and only the constants are on the right side. So row 1 would be x minus 2y. We would need to add this 4z over. So plus 4z equals 6. X, I need to add over the y, plus 13z equals 6. And then the last one was already in order. Okay, once we get it put in standard form, we're going to make our matrix. And identifying these, we have row 1, row 2, and row 3. You can see why the R's now for rows. So just like we did with the equations, we're going to start by making our x coefficient of 1, which it already is. And then we're going to work our way down and eliminate the x's below. So the first thing we're going to do is take negative 1 times row 1 and add that to row 2 to create a new row 2. That means we're not changing row 1 and we're not changing row 3. But when I get here to row 2, I'm going to do negative 1 times 1 is negative 1 plus 1 would be 0. Negative 1 times negative 2 would be 2. 2 plus 1 is 3. And then negative 4 plus 13 would be positive 9. Negative 6 plus 6 would be 0. And now I'll move my focus to this negative 2. If I could add that to a 2, it would disappear. So I'm going to copy over my first 2 rows because I'm not going to change them. But row 3, I'm going to do negative 2 times row 1 and add it to row 3. Sorry, I don't need a negative, just 2, since this is already negative. So 2 plus negative 2 is 0. This would be negative 4 plus 6 is 2. This would be 8 minus 1 gives me 7. And 12 minus 10 gives me 2. Okay, so my first column is good. Have an X in the first row and zeros underneath. Now I shift my focus to the Y in the second column and second row. That needs to be a 1. So my first row is no longer going to change. My bottom row is not going to change right now. But my second row, I need to turn a 3 into a 1. So divide it by 3 or multiply 1/3 times row 2. So they give me 0, 1, 1/3 times 9 is 3, and 0. And now I move my way down again. This needs to be 0. So I do negative 2 times row 2 plus row 3. So not changing rows 1 and 2. but multiplying -2 times row 2 and adding that to row 3. Would be 0, 0. This would be -6 plus 7 is 1 and 2. So my next step would be to make this bottom value a 1 if it's not already, but it is in this case. So as soon as you have a diagonal of 1s going down the middle and all 0s in the bottom left corner, you have finished solving the system to the point that we want to right now. And this particular form is called row echelon form. In row echelon form, you still have to do some algebra to finish the problem, but this bottom right corner tells us what we knew from before. Z is equal to 2, part of our solution. Row 2 tells us that y plus 3z equals 0, or y plus 3 times 2 equals 0, that'd be 6. So y is -6. And then the first row of our matrix tells us x minus 2 times y plus 4 times z equals 6, or x plus 12 plus 8 equals 6. That'd be 20. Subtracted would be x is -14. So we get our solution, -14, -6, 2. And that took up quite a bit less paper, and it's easier to work with when all you have to do is focus on the numbers and the coefficients. So we're going to continue from here and do what's called Gauss, G-U-A-S-S, Gauss-Jordan method. The Gauss-Jordan method replaces that last part we just did, back substitution, with more elimination. So continuing where we left off, we had 1, -2, 4, 6, 0, 1, 3, 0, 0, 0, 1, 2. To get in row echelon form, we focused on this bottom left-hand corner being zeros and the diagonals of 1. Now to complete Gauss-Jordan method, you work your way back up and make the upper right-hand corner also 0. So we went down each one of these columns, and now we're going to start with the Z column and work our way back up and make those all zeros. So for this first run through, we're not going to change row 1 or row 3. But row 2 has a 3 right here that I want to eliminate using that bottom 1. So I'm going to do -3 times row 3 and add it to row 2. The nice thing about this is you have a bunch of zeros. So 0 plus 0 is still 0. 0 plus 1 is still 1. -3 plus 3 is 0. -3 times 2 is -6. Plus 0 gives us a -6 there. Continuing with that same column, we're going to go up and get rid of this 4. So this time we're going to be changing row 1. So I'm not going to copy it over yet. Row 1 has a 4 in it, and I want to use the 1 at the bottom. So if I can make that a -4. So we'll do -4 times row 3 and add it to row 1. So 0 and 1 is 1, 0 and -2 is -2. -4 plus 4 is 0. -4 times 2 would be -8, plus 6 would be -2. And then the last thing we need to do is make this -2 a 0. For that, we will use the 1 in its column. So we're going to be changing row 1 again, not 2 and 3. Let's copy those over. And for row 1, I need to do 2 times row 2 plus row 1. So 0 plus 1 is 1. 2 plus -2 is 0. 0 plus 0 is 0. -12 plus, sorry, -2 is -14. Now this form, where all you have is the diagonal of 1s and everything else is 0s, is called reduced row echelon form. And in that form, you get all 3 variables values. You get that x is -14 from the first row because there's a 1 in the x column. There's a 1 in the y column. Y is equal to -6. And z is equal to 2. So this last portion we did here replaces the substitution we did in the previous method. So one of the nice things we are able to do is using a calculator to solve systems. When you do this, it involves using matrices, so you have to understand how it works by hand, and that helps you better understand the calculator method. So we're going to do this system, x minus 2y plus 3z equals 7, 2x plus y plus z equals 4, -3x plus 2y minus 2z equals -10. We're going to create our augmented matrix. Using the coefficients, since everything is already in standard form. And then we're going to go through a series of steps on the calculator. So let me bring up my calculator view. Okay, these steps are on one of your formula charts, and I also have them written in the notes for when you go back to the handwritten notes. But you start by accessing the matrix menu, which is above the x to the -1 button. So you have to push second, x to the -1, which is matrix. And then we need to go over to edit so that we can edit the matrix. When you go to edit, you can choose any of these letters. They're just names of the matrices. So I'm just going to start with A. So now you see at the top it says matrix A, and then you have a cursor flashing on 1 times 1. That is supposed to be your row and column size. So for the matrix we're working with, we had 3 rows. So I'm going to type a 3, and the easiest way to do this is push enter after every entry, and then 4 columns, push enter. And that created the boxes that you see on your augmented form. And now you need to go through and input the coefficients, again, pushing enter after every one. So have 1, -2, 3, 7, and then it moves down to row 2, 2, 1, 1, 4. Row 3 is -3, 2, -2, -10. And you can arrow through there and scroll back and forth and make sure that you put them in correctly. After you get them input, you need to quit completely out of the matrix application. So you push second and the mode button for quit. And that's what forces the calculator to save your matrix. Now we're going to go back into the matrix menu. So second matrix. and we want to do math. So we're going to go over to the math menu. And if you scroll down through this menu, you'll see a lot of things you don't understand probably, but there is one, option B, that is what we just learned, RREF, or reduced row echelon form. So I'm going to arrow down to that and hit enter. And this says, what do you want me to do reduced row echelon form on? This is where I need to input the name of that matrix. So I'm going to push second matrix, and I'm just in my list of names. So option number 1 is the matrix I want it to work on. Push enter, and out pops my solution. So let me go back to my notes page to show you what you should write down. Okay, so there are the steps that we just went through to input that into our calculator. The output that came up on the screen after I did RREF of matrix A was the reduced row echelon form with 2, -1, and 1 as the coefficients. So interpreting that means X is equal to 2, Y is equal to -1, and Z is equal to 1. Or we could write it as an ordered triple for our solution, 2, -1, 1. Okay, so let's try another one of those. This will officially be example 3. Here's the system. This throws in a 4th equation, but once you've gone to the matrix form, it doesn't really matter how many equations there are. It's not any more difficult. So first thing we're going to do is make our augmented matrix. It will have 4 rows because I have 4 equations. The first column will be the X coefficients, then the Y coefficients, the Z coefficients, and the constants. Okay, and I'll switch back to the calculator. So I need to input my matrix, so second matrix, and I need to edit, remember, is the first thing. So matrix A is the matrix we just solved, so you could clear that out, or you can just move down to B and make that our new one. Our new matrix has 4 rows and 4 columns. And now inputting the coefficients. After you input the coefficients, you need to force it to save with second quit. And now we want to run reduced row echelon form. So that's in second matrix. Go over to the math menu. Oops, pushed the wrong button. Reduced row echelon form is option B. And this time I want to work on matrix B. So second matrix, matrix B. And this solution is not so pretty because the answers are fractions. So when you're working with a TI-84, if you end up with decimals that are not repeating or ones that you don't recognize as a certain fraction, like 0.3 repeating is 1/3, if you will push the math button, and the very first option has an arrow and then says frac, that is saying change it to a fraction. So if I just push enter, notice it populated answer in front of that. So it's saying whatever my last answer was, make it a fraction, and that's a much prettier solution. So let's switch back to our notes and write those down. So when I did RF B, this was my solution matrix. With all the ugly decimals. Sorry, this was a 0. So then on our calculator, we push the math button and chose the option to fraction. And that turned our matrix into a prettier answer. With 11/7, -2/7, 1, and 0. So because our system had 4 equations, but only 3 variables, that bottom row in a case like that should end up as all zeros. If it does not end up with all zeros, that means you don't have a valid solution. So you have to be sure that you check that at the bottom. But the first row still means that for our solution, the x value is 11/7, y is -2/7, and z is 1, because we double checked this. We got 0 = 0 basically, which is true. So that means we have a good, valid solution to our system. Okay, example number 4. This is our system. Turned into a matrix. I will trust that you will go through the steps and practice this. If I do reduced row echelon form on whatever name you give this matrix, I did it as A. This is the solution matrix I got. So this solution is saying that x is equal to 0, which is fine. Y is equal to 0. They can be 0, that's fine. But the bottom row says 0 is equal to 1, which is false. So this is a system that has no solution. And remember, we called that inconsistent. This is inconsistent with what we know about our numbers. 0 is not equal to 1. And finally, example number 5. Here's our system. Turned into the augmented matrix. Notice there's no x in the bottom equation, so you populate that element with a 0. There's our matrix. If you put that into your calculator, run reduced row echelon form, here's your solution matrix you should get. So interestingly, on this one, we didn't actually end up in reduced row echelon form because we don't have a diagonal of 1s and everything else is a 0. So we have to interpret this solution a little bit more complicated the first row is saying x plus 5z equals negative 15. Y plus 2z equals negative 12. And then the bottom row, 0 equals 0, being a true statement. In this situation, what you're getting is infinitely many solutions. These two answers, y and x, depend on what z is. So here we end up with infinitely many solutions because the x and y values depend on what z is, and that's where that name dependent system comes from. Because both x and y depend on the value you substitute in for z. So if I wanted to solve that, I have x plus 5z equals negative 15. I could get x by itself by subtracting 5z. And then my second equation, I can subtract 2z to get y by itself. So my solution would be negative 5z plus 15 for x, negative 2z minus 12 for y, and z can be anything you choose because the bottom row was just 0 equals 0. So as an example, if I chose z to be equal to 1, if I plug a 1 in here, I would have negative 5 plus 15. Sorry, should that be a minus 15? It should be a minus. So that would be negative 20. And then negative 2 minus 12 would be negative 14 with a z value of 1. Maybe I choose z to be 4. So 4 times negative 5 would be negative 20, minus another 15 would be negative 35. 4 times negative 2 would be negative 8, minus 12 would be negative 20, using a z value of 4. So z can be anything, and x and y depend on what that is set to.